In this video, we solve a third order ordinary differential equation using variation of parameters. We're going to use, some formulas that we derived earlier in the last video. If you want to see where these formulas come from, check out the video on the derivation of the formulas for variation of parameters for third order ODEs. I did a video deriving the formulas for second order ODEs as well, but I made a second video for third order ODEs. So you might want to check that out so you know where these formulas come from and why we're able to do what we're about to do. So let's say I'm asked to solve this third order ordinary differential equation. It's non-homogeneous. Now, since the corresponding homogeneous equation has constant coefficients and the right-hand side is just an exponential function, the most efficient way to solve this would probably not be variation of parameters. I would probably use method of undetermined coefficients. But I wanted to give you an example of how this works. So we're going to apply this method here, even though that's probably not the most efficient method for this particular differential equation. So let's practice this method for this third order differential equation. First thing we do anytime we're solving a non-homogeneous differential equation is we solve the corresponding homogeneous equation, which looks just like this. You just set that right-hand side equal to 0. And since this has constant coefficients, we can let y equal e to the mx. We know that derivatives of exponentials yield other exponentials. And if we take the right exponentials and we multiply them by constants and add them together, the constants could be such that we get a 0 on the right-hand side. So this is a good guess for the form of that solution, and it turns out to work every time. If we let y equal e to the mx, then the derivative of y is m times e to the mx. So the derivative of an exponential is that exponential times the derivative of the inside by the chain rule. And then we take the derivative of the exponential again, times the derivative of the inside by the chain rule, so we get another m. And it's a third order differential equation, so we take the third derivative. And that leads to another factor of m because we're applying the chain rule. So we compute the first, second, and third derivatives, and then we substitute into the differential equation. And so you get this. We end up with m cubed times e to the mx minus 3 times y prime, which is just m e to the mx, plus 2 times y, where y is e to the mx. And we're setting that equal to 0. And so we factor out e to the mx here, and we get this. So this exponential times this polynomial must be 0 if this exponential is going to be a solution to the differential equation. Now this exponential is never 0. So we must have that this polynomial is equal to 0. The exponential is going to be greater than 0 for all real numbers x. This is called our characteristic equation. It's what we get after we substitute into the differential equation and simplify and divide out that e to the mx, if you want to think of it that way. A lot of teachers will skip from here to here, and that's totally fine when you get beyond my class. But in this class, I really want to see that you know where that formula comes from, because the students would go from here to here and then they would write down the answers, but they really didn't know where this came from. This comes from the fact that y is equal to e to the mx. So I want to see these steps on your quiz over this material, just to ensure that you know, that you can show me that you know where this formula comes from. It's just a logical conclusion of letting y equal e to the mx. So now you want to solve this equation. Now, if it factored easily, you would just factor it If you could factor it by grouping, you would factor it by grouping. If it doesn't, then we usually go to possible rational roots to identify a root of the equation. And then once we know a root of a polynomial equation, we know a corresponding factor. So this one doesn't factor easily. So I would look for possible rational roots. Because if I have a root, I know what a factor is. Know what the corresponding factor is. Now, the possible rational roots of a polynomial equation are given by the factors of the constant term divided by the factors of the leading coefficient. And the factors of the constant are the factors of 2, and the leading coefficient is an implied 1. So we actually don't have very many possible rational roots this time. 1 times 2 is 2, and -1 times -2 is positive 2. So we got plus and minus 1 and plus and minus 2. Factors of 1 are plus and minus 1. So the possible rational roots of that polynomial equation are 1 and -1, 2 and -2. Taking each of those and dividing by that 1, but since dividing by 1 doesn't do anything, we just end up with those numbers from the numerator of that like fraction-like expression that I've written here. So we found the possible rational roots. Now you want to just try one. You're trying to find a value of m that causes that equation to be 0. That's called a root of that polynomial. So we are just trying values of m from this list until we find a root. And we'll call that m equals k just for example. You're trying these possible roots until you get a root. I think m equals 1 is going to work. So I'm going to try m equals 1. Well, I'll have 1 cubed there minus 3 times 1 plus 2. That's 1 minus 3 plus 2. And that's 3 minus 3, which is 0. And that's great. That means that m equals 1 is a root. Now, this is a fact about polynomials. If x equals k is a root of a polynomial, let's just call it p of x, then x minus k is a factor of p of x. So if I call this p of m, oops, here we go. Call this p of m. M equals 1 is a root, implies that m minus 1 is a factor of p of m. Now, in order to find out how p of m factors in general, I want to factor this cubic polynomial. I'd like to divide out that linear factor, m minus 1, and I'll do so using long division. So we'll put p of m in the numerator here, and the factor that we're dividing out in the denominator. Now you want to include all of the powers of m, starting with the highest power of m, and you want them in descending order. So we've got that m cubed here. Then I want an m squared term. I actually don't have an x squared term, so I'll add in a 0m squared. Then I want an m term, which is that negative 3m. And then I want the constant term there. So I've got this polynomial divided by m minus 1, and that's going to equal some quotient. I'll call that q of m. In order to find that quotient, I will use either long division or synthetic division. I'm going to use synthetic division. If you prefer, you can use long division. That's totally fine. But in order to get this factored further, we want to say m minus 1 times what gives us this, or this divided by m minus what is what quotient. Now, so this is equivalent to saying that P of M, that's the polynomial in the numerator, is equal to M minus 1 times the quotient. So we need to find that quotient, and I will use synthetic division to do that. And if you don't like synthetic division, that is okay. You can use long division instead. Now, when you're using synthetic division, you take this expression in the denominator, if it is m plus or minus a constant, or x plus or minus a constant. You set that equal to 0 and you solve for x or m. That's going to give you the root that corresponds to that factor. So we set that equal to 0 and we get m equals 1. That goes in the little box over here. Then the coefficients of our polynomial in the numerator, they go over here. So there's a 1, a 0, a -3, and a 2. And you bring the 1 down, and then you multiply, and then you add, and multiply, and add, multiply, and add. Now these are the coefficients of Q of M. Now to figure the degree of Q of M, you have to look at the degrees of this guy and this guy. Since this is degree 3 and this is degree 1, and you're dividing it out, the degree of Q is 3 minus 1. You always take this degree and you subtract this degree to find the degree of the quotient. So P of M, that's this polynomial in the numerator, turns out to be m minus 1 times Q of M, where Q has these coefficients, and Q is a second degree polynomial. So we have Q equals 1m squared plus 1m minus 2. Now this is equal to 0 because we're solving the characteristic equation. The left-hand side factors this way, and that characteristic equation involves that polynomial being set equal to 0. So we found Q of M. We write that polynomial as that factor corresponding to the root times Q of M. And then you want to factor Q. Or in other words, you're just trying to factor this as much as possible. Now, if this is quadratic and you don't know how to factor it, you can always use the quadratic formula. So I'm looking for two factors that multiply, or two numbers here that multiply to give me -2 that add to 1. 2 and 1 will work if the 2 is positive and the 1 is negative. So this is the factored form of that characteristic equation. Notice that m minus 1 appears twice. So that's m minus 1 squared times m plus 2 equals 0. Since that's squared, that means we've got a repeated root there. So the first root is m equals 1, but it's repeated. So we'll say that m1 and m2 are both equal to 1. And then we've got a third root over here, and that comes from setting this equal to 0. So m sub 3 equals 2, or -2. Now remember, if you've got a repeated root, the first solution is e to the m1x. That's just e to the x in this case. And the second linearly independent solution can't be e to the m2x because m2 and m1 are the same. So you have to take this guy and multiply by an extra x. That x comes from reduction of order. We could prove that that was the second solution given that solution using reduction of order. And that's our second linearly independent solution corresponding to that repeated root m equals 1. Then the third linearly independent solution is e to the m3x. So we've got that. Oh, I was about to write general solution. It's not the general solution. Now we are ready to write down our y sub c. Since the homogeneous differential equation, the corresponding homogeneous equation was third order, we get 3 terms. So you've got c1 y1 plus c2 y2 plus c sub 3 y sub 3. Okay, now we were solving this differential equation and we wanted to use variation of parameters. So typically we'd go back up to the differential equation and we would make sure that there's a 1 in front of that y triple prime. There is, so that means the right-hand side is what we have been denoting as f of x. Now, if there's not a 1 here, you've got to divide out that function, and that's going to change the function on the right-hand side. After you manipulate the equation so that you've got a 1 in front of that highest order derivative, f of x is the function on the right-hand side. Okay, so now we're ready to do a variation of parameters. So we're going to let y sub p equal u1 y1 plus u2 y2 plus u3 y3, where u1, u2, and u3 are non-constant functions. That way, y sub p is linearly independent from y sub 1, y sub 2, and y sub 3. Now, this is the one method where I'm going to let you skip some steps because, as you have seen, deriving these formulas is pretty involved. We end up with these expressions involving 18, 20, 40 different terms set equal to a function of x. So we're going to skip some of those steps, but you should make sure that you understand the derivation of these formulas that we're about to use. We said if y sub p is a solution to the non-homogeneous equation for unknown functions u1, u2, and u3, if we take the first, second, and third derivative and substitute into the differential equation, and we make some assumptions about a couple of equations involving u1 prime, u2 prime, and u3 prime, then what falls out of that is that we end up with another equation involving u1 prime, u2 prime, and u3 prime. So we've got 3 equations with 3 unknowns, and we're trying to, or we can solve that system of 3 equations and 3 unknowns using Cramer's rule. Cramer's rule leads to these results. So we'll say let y sub p equal this, then by variation of parameters, u1 prime is equal to w1 over w, u2 prime is equal to w2 over w, u3 prime is equal to w3 over w, where w is the Wronskian of y1, y2, and y3. So you've got those 3 linearly independent solutions in the top row, and you take their first and second derivatives to make a 3 by 3 matrix, and then you evaluate that determinant. Now in our case, our first solution was e to the x. So the first and second derivative of e to the x are e to the x. Now the second function was x times e to the x. Now, according to the product rule, I'm just going to do this as side work. The derivative of a product is derivative of the first times the second plus derivative of the second times the first. And if you factor out that e to the x, you get 1 plus x times e to the x right there. And then if we want to take the second derivative of that, we can use the product rule again. We have the derivative of the first times the second plus derivative of the second times the first. We've got 1 plus x plus another 1 is 2 plus x times the exponential there. All right. Now our third solution was, what was that? It was e to the negative 2x. So we get e to the negative 2x times the derivative of the inside, and then e to the negative 2x times the derivative of the inside again. So we're going to multiply by another negative 2, so we get a 4. And so now you've got the determinant of this 3 by 3 matrix, that's the Wronskian. So we'll have the formulas for U1 prime, U2 prime, and U3 prime. And then we're going to compute W, W sub 1, W sub 2, and W sub 3. Okay, now you can expand along any row or column that you like. I think I will expand, like which one will lead to the simplest results? I think it'll be easiest if we expand along this column. So we'll have plus, minus, plus as the sign convention, excuse me. So the Wronskian is equal to positive 1 times e to the x. And then we cross out the row and column containing e to the x, cross out these guys, and then you've got that times, or you've got that there, this 2 by 2 determinant. I'll just write down the determinant and we'll evaluate it in a minute. And then we're subtracting e to the x times, and then you want to cross out the row and column containing e to the x, or this middle e to the x, and you've got an x e to the x, e to the negative 2x in the top row, and 2 plus x e to the x, and 4 times e to the negative 2x in the bottom row. And then for the last one, we've got e to the x times. We cross out the row and column containing that last e to the x, and we've got this guy right here. Okay, now let's evaluate these. So I've got e to the x times this expression. I have 4 times the 1 plus x is going to give me a 4 plus 4x. And e to the negative 2x times e to the x is an e to the negative x because you're adding those exponents. Then we're subtracting something negative. So I'm going to add 2 times the 2 plus x. That's going to give me a 4 plus 2x times another e to the negative x. So that's that first piece. Then over here, I'm subtracting e to the x times these guys. I've got a 4x, and e to the x times e to the negative 2x is e to the negative x. And then I'm multiplying these two guys together and subtracting. So I'm subtracting 2 plus x times e to the negative x. And then for the last one, I've got e to the x there. I'm doing this times this, minus this times this. Now you can simplify some of these steps if you want to. That's totally fine. If I take this exponential and I multiply it through here and here, this is going to reduce with that when I distribute, and that. These guys are going to be gone. And I'll just end up with a 4 plus x, or excuse me, 4 plus 4x plus 4 plus 2x. And if I distribute this negative e to the x here, I've got a minus 4x. Negative times a negative is going to be a positive 2 plus x. And those exponentials cancel again there and there when we distribute. Similar things happen here. That should be a negative. So we end up with a negative 2x minus 1 minus x. Okay. These guys reduce, and these guys reduce, and these guys reduce. And so we're left with 8 plus 2 is 10, minus 1 is 9. So after all that, the Wronskian is 9. Okay, not bad. Now for W1, you're going to use the almost identical determinant, but you're going to replace that first column with 0, 0, and f of x. Now our f of x was negative 4 e to the negative x. It's the right-hand side of that differential equation when the leading coefficient is 1. So we've got 0, 0, and negative 4 e to the negative x here. And the other two columns stay exactly the same. Now I would expand along this column. It makes the most sense. It's got all those zeros in it, plus, minus, plus. So we've got 0 times a 2 by 2 determinant, which is going to be 0, minus 0 times a 2 by 2 determinant, which would be 0, plus this negative 4 e to the negative x times this 2 by 2 determinant. So we end up with negative 4 e to the negative x times this, which is going to give me a negative 2x e to the negative x, minus this times this. So we're subtracting 1 plus x, and then e to the x times e to the negative 2x is e to the negative x. Now if I distribute that negative, we end up with this. I've got negative 1 times an e to the negative x, and then I've got a minus 2x and a minus x, that's minus 3x times e to the negative x. So this times negative 4 is positive 4 plus 12x times e to the negative 2x. Okay, let me check my signs. That looks right, and this negative times that negative is going to be positive. Okay, checks out. All right, that's our W1. So we computed W, which took a little bit of time. Then we computed W1. Next, we will compute W2. Which is very similar. You just take the Wronskian and you swap out that third or that middle column for 0, 0, and f of x. So our first one was just e to the x, e to the x, and e to the x. The second column is now 0, 0, and negative 4 e to the negative x. And the last column is this. Oh, this one's going to be nice and easy to do. The other ones aren't bad, it's just algebra. But it just takes a little bit more time. So we'll expand along this column because it's got all the zeros in it. Remember the sign convention, you start plus, minus, plus. Then you go pick up where you left off, minus, plus, minus, and plus, minus, plus. Now I ignore all these signs out here. I only keep the signs for this sign convention on the column that I'm expanding along. So I have a minus 0 times a 2 by 2 determinant, which is 0, plus 0 times a 2 by 2 determinant, which is 0. And then we're subtracting something negative. So that's going to be adding. So it's going to be 4 times e to the negative x times. We cross out this row and this column, and we evaluate this 2 by 2 determinant. Probably could have done that all in one step. I have 4 times e to the negative x, and then here we've got negative 2 times e to the negative x, and we're subtracting, multiply here, e to the negative x. So I've got negative 3 times e to the negative x times 4. That's negative 12. And e to the negative x times e to the negative x is e to the negative 2x. Now w sub 3 comes from taking our Wronskian, leaving the first two columns alone. And then replacing that third column with 0, 0, and f of x. Now due to our sign convention, again, that's plus, minus, plus. And we get this. Cross out this row in this column, and then you've got that negative 4 e to the negative x here. And then you're evaluating this 2 by 2. So you're going to have this times this. So it's 1 plus x times e to the 2x minus this times this. And if you distribute that e to the 2x, what you'll find is We've got two terms that reduce, which is nice. Always nice when they cancel. And we end up with this. -4 times e to the x is our W3. All right, almost done. So you can tell why I let you skip steps, because even when we do skip steps, this problem takes at least, this is the halfway through the third page. U1 prime is then W1 over W, and that came from Cramer's rule, and W1 turned out to be 4 plus 12x times e to the -2x, and W happened to be 9, which is just a constant. So if I want U1, I just take the antiderivative of U1 prime, and I think I'll factor out that 1/9. Since I've got a polynomial times an exponential function, the easiest way to evaluate this antiderivative is using the tabular method. So this is my u, and then everything else is dv. And then we take the derivative twice. And then you take antiderivatives until you catch up with all the derivatives. You want the same number of rows in both columns. So the antiderivative of e to the -2x is e to the -2x. Now, if you were taking derivative, you'd have to multiply by -2. And you take an antiderivative, you've got to divide by -2 because you are undoing that. And then we're going to do that again. So we're going to have an extra -1/2 out there again. So we'll have a 1/4 there. And then you've got a sign convention, plus, minus, plus. So you multiply across the diagonals. You do this times +1 minus or plus this times -1 plus c. So we get 1/9 times all of this. -1/2 of this is going to give me a -2 plus 6x times e to the -2x. And then we'll have 12 times 1/4 is going to be 3 times the -1 is -3 times e to the -2x, plus a constant of integration c. Now, traditionally, when I use tabular integration, I don't simplify, but we do tend to simplify y sub p. So I might simplify this one this time. We're going to choose c1 to be 0, because we don't need a constant times y1 as part of our y sub p. And then everything else here, going back to this line of reasoning, I've got -2 of these minus 3, so that's -5. And then I have a -6x there times the e to the -2x, and that's u sub 1. And if you want, you could factor out the negative as well. I would probably do that. Okay. So we state the formula for u sub 1 prime, and then we compute u sub 1, and we choose the constant of integration to be 0. And now we're going to do the same thing for u sub 2. U sub 2 prime is equal to W2 over W. Now W2 is -12 e to the -2x, and W is 9. So that's -4 times 3 over 3 times 3 times e to the -2x. So those 3's reduce. So that means our u sub 2 is the antiderivative of -3 or 4/3 e to the -2x. And we're dividing out a -1/2. Because if you take a derivative by multiplying by -2, you take an antiderivative, you're going to have to divide to undo that. So we'll get this. We'll choose this constant of integration to be 0 as well. So we have the formula for u sub 2 prime. We compute u sub 2, and we choose the constant to be 0. So this is our u sub 2. It's just not simplified. So I will simplify that. That's going to be 2/3 times that exponential there. Okay, and then we're going to find u sub 3 prime. That's w sub 3 over w. And w sub 3 was -4 e to the x. Well, that's the nicest, easiest one to solve. So u sub 3 is the antiderivative of this, which is just the same function plus a constant, and we'll choose the constant to be 0. So we state the formula for u sub 3 prime. Then we compute u sub 3, and then we choose the constant to be 0. Okay, so now we've got u sub 1, u sub 2, and u sub 3. And remember, the goal was to find y sub p. So y sub p turns out to be u1 y1 plus u2 y2 plus u3 y3. And u1 is this function here. So -1/9 times 5 plus 6x times e to the -2x. And y1 is this exponential e to the x. Then u sub 2 is 2/3 e to the -2x. And y sub 2 was x times e to the x. And u sub 3 was -4/9 e to the x. And y sub 3 was e to the -2x, if I remember correctly. It's been a while. Yep, that's e to the -2x. So this is my u1 y1 plus u2, and this piece is y2, plus u sub 3, y sub 3. And then we're going to simplify from there. So we've got, if you multiply these two guys together, you end up with an e to the -x. And if you multiply these two guys, you'll get an e to the -x here and 1 over here. So we end up with a bunch of e to the -x's. So I'm going to factor that out from everything, and then just look for those coefficients. So I've got -5/9 minus 6/9 times x. And we could simplify that, but I'll leave it that way just in case it might help me later. Then I've got a 2/3 x here. So maybe I will call that plus 6/9 times x. So it'll have the common denominator with that one. And then I've got a minus 4/9 over there. And that's it. I have 2 terms, 1 term, and then 1 term. So that's it. And these guys reduce. And I've got a -5/9 here and a -4/9 there. So there's just a -1 of those. Okay, so that's our y sub p. Wow, that was pretty involved to get y sub p. So we substitute u1, u2, u3 into the form of y sub p, and we simplify. And then once we do that, we can write down the general solution. The general solution is y equals y sub c plus y sub p. So that's c1 y1 plus c2 y2 plus c3 y3 plus y sub p. And these are all well defined for all real numbers. So this will work for all real numbers. Okay, so that is the method with the steps skipped. Still 3.5 pages. So we are starting from first principles. We say this, or we did not start from first principles this time. We skipped some steps with variation of parameters, but we say, okay, let's look at this. Let's solve the corresponding homogeneous equation. So we do that from first principles. We get to this characteristic equation. You find a root, you find a corresponding factor, you divide out the factor to get the quadratic polynomial factor that's remaining. You factor that quadratic, and then you find the roots of the characteristic equation, and then you find the corresponding fundamental set of solutions given those roots. And then, or a fundamental set of solutions given those roots. So you've got these guys, and you multiply them by constants and add them together, and that's your y sub c. Then you say, okay, y sub p has to be this. Now, according to the derivations that we did in the last video, u1 prime, u2 prime, and u3 prime satisfy these equations where w1, w2, and w3 are given by this. You take the Wronskian of those three functions that form your fundamental set of solutions for the corresponding homogeneous equation. And to find w sub I, you replace the ith column with 0, 0, and f of x. So for w sub 1, you replace the first column with 0, 0, and f of x. For w sub 2, you replace the second column with 0, 0, and f of x. And for w sub 3, you replace the third column with 0, 0, and f of x. So we work out the Wronskian. We find it. We find w1. We find w2. We find w3. Then we state u1 prime, and we compute the antiderivative to get u1 back. We state u2 prime, and we compute the antiderivative to get u2 back. Then we state u3 prime and compute the antiderivative to get u3 back. And then we just substitute u1, u2, and u3 into the form of y sub p and simplify, and it turned out y sub p was really simple. So the general solution is this. Now, let's look at that differential equation. If I see this on an exam, I would never use variation of parameters here. This is a constant coefficient differential equation, and the right-hand side is an exponential. So we could have just guessed at the beginning that y sub p equals a constant times e to the negative x. And then we would have found out that that constant turned out to be -1, because that's your y sub p. And then we would have gotten here pretty fast. But I wanted to show you at least once how we apply the method to a third order differential equation. Now, if the right-hand side were not an exponential function, but if the right-hand side were something other than an exponential, a sine or a cosine, or a polynomial, or a finite sum or product of those, or if the corresponding homogeneous equation did not have constant coefficients, then we would have to use variation of parameters to find y sub p. So this is just our first example. We will do another example of this. I think I'll do another example and put it in the videos once we've studied Cauchy-Euler differential equations. That's a method that'll allow us to solve different homogeneous differential equations of a certain form.